And then I will hand over the word to Lewis. The stage is yours.
Right, thank you very much, Laura. Yeah, and thank you for this really warm welcome. It's indeed a pleasure to be speaking today, and also to join IFADO this month. I have to say that the welcome has been beyond my personal expectations, and you've even given me a really nice office with a really nice window view of Dortmund. So what can I say, right? So before we begin, I'm just going to give us very quickly an overview of what I'll be speaking on today and my assumptions or my premises. So I'm going to assume that as humans, we have limited capacity to process information, and hence it is absolutely necessary for us to select which information to process when for the task that we have at hand. Now, in order to address this, we could either be looking at human perception, how we take up information, or we could also be looking at human cognition in terms of how we might actually be processing this information with our nervous system. Another premise, or something that I like to put forth, is that performance alone may not be diagnostic of information processing, especially in our current day and age where we are moving more and more towards human-machine partnerships, hence the requirement or the increasing importance of neuroergonomics as a discipline. And of course, my talk today would allow us to discuss very quite openly how human-machine interactions are currently and increasingly being redefined from those relationships and interactions of control to those of partnerships with emerging trends in artificial intelligence and computer vision, for example. So let's begin. And I would like to take as my starting inspiration this perspective from Alan Newell, which is that we could always be considering information processing in terms of time scales, right? Hence the image that I used to grace my title slide. Now, if you're a hardcore neuroscientist who only believes in biological information processing, then really information processing for you might stop there, right? To say that, well, the skill of neuroscience or our nervous system is such that spans over hundreds and thousands of years, and not very much has changed, to be perfectly honest. And with this perspective, animal models as a way of understanding how the nervous system works is a viable option because not very much has changed with regards to how neurons communicate information. Now, the other perspective that we could take as well is something quite remarkable. The fact that in spite of this position that very little has changed with regards to our nervous system over hundreds and thousands of years or even millions of years, this nervous system still enables us to interface and deal with engineering advances that changes very rapidly over the span of 3 to 10 years, right? So every time we experience an evolution or a disruption in technology, nonetheless, our fundamental information processing system is capable of dealing with it. To take something quite natural, that we've taken for granted, reading and writing, for example, a language, couldn't possibly have had more than 3,000 years of emergence as an innovation. And yet this nervous system is capable, more than capable of picking up reading and writing. Now, how are we able to achieve this? Now, one possibility is our psychology, our ability to make use of psychological concepts and ways of reframing information from the outside world in a way that is understandable for our nervous system. Okay, so the reason why I present this is also to show that we are rapidly moving towards a future where we might be treating machines as partners. And in order for us to achieve advances in that, it might be very useful for us to understand information processing across all these different timescales. I see the work that I do as being in the intersection of psychology, neuroscience, and engineering as a result of that. And that's what I'm going to be sharing today. So here's a couple of snapshots of my career. So I started off being interested in the fundamentals of object recognition, or more specifically, visual object recognition, so in psychophysics. But the more I got in touch with technology, the more I became interested to understand, well, can we be tailoring technology in order to support information uptake? For example, if a computer system is aware of where our eyes are looking or where we might be pointing, can it be modifying the information environment to support our ability to either look at images or to look at text? I started to get involved in work related to teleoperations or remote operations of unmanned aerial vehicles. And then came a really crazy grant, MyCopter, which had the mandate of how could we make flying as easy as driving a car, before we got back to Earth and started looking at automated vehicles instead, to situations like this where we ask questions such as, how can we do task switching effectively between, let's say, reading and writing, back to steering a vehicle in the age of automated vehicles or semi-automated vehicles. Now, since I joined LMU, or the Department of Media Informatics at LMU, we've been looking at other instances of how we could be augmenting the real world environment with added information to support, let's say, cyber physical systems or haptic assembly. I've also been looking at how we could be making use of everyday devices like the mobile phone to support our ability to pick up information from the environment, such as the case grammar of different objects in the world. So let's go back about, let's say, 14 years or so, where I started off doing my PhD in Tübingen at the Department for Biological Cybernetics, or the Max Planck Institute for Biological Cybernetics, where we were highly motivated by the discipline of cybernetics, which is to study and to understand control and communication in the animal and the machine, right? So if you're a fan of cybernetics, then you would think of all problems or all relationships in terms of systems. And if you think of it in this fundamental way, you would be able to say that, well, do you know what? A system, a feedback loop system like this could characterize many human-machine relationships regardless of the machine in question. And well, here's someone that we know quite well, also enjoying the use of his machine. But what's really important is for us to understand how the human sends an instruction to the machine, which changes the system state to a new state that is beyond what the human can achieve in and of itself. How is this new state reported back to the human that allows the human to compare it with the current goal? And in perceiving this difference in the human's goals and the actual state, what we call the error signal, to update the instruction sent to the machine again. So this is a very simple feedback loop. And if we take this perspective, we could be analyzing the whole system in the frequency domain. Engineers can be giving us transfer functions of the machine itself, or approximations of how information is transferred from the input to the updating of the system state. But then there remains this question of what could we characterize the human to be? What's the transfer function, the information transfer function of the human, right? So for example, if the human is trying to fly a plane by looking at the outside world or by looking at an instrument. So if we take this approach, we could be looking and comparing between how humans might perform if they had the entire outside world to fly by, or if they had a single instrument, right, the attitude indicator to fly by. And we can approximate the human performance as a transfer function in the frequency domain that's defined in terms of gain, which as psychologists, we might anecdotally refer to as attention, or time delay, the amount of time it takes before the error signal, which is perceived, results in a delay in time. And we could characterize this in the frequency domain across the entire spectrum, okay? Now, the nice thing about taking this approach, I will exemplify here, is that if we didn't consider this as a system in the frequency domain, all we would have would be performance, which would be error variance, which would show that performance actually gets worse as the wind disturbance in this task, for example, it increases, okay? But it would show that we consistently do worse, or we control this helicopter worse when flying by relying on outside world visuals compared to looking at the instruments. Now, the nice thing about modeling or characterizing the human information transfer system as a transfer function and trying to fit these parameters is that it allows us to extract an invariant of the characteristic of the human operator as an information processing unit. So regardless of the difficulty of the task, from easy, medium, or hard, what you would see is that across these two different systems, the gain, or KP, afforded by the outside world is almost always less than if you were flying by an instrument instead, regardless of the disturbance itself. So we're able to, by modeling, extract an invariant or a characteristic of the human operator. Okay, you would also show that the time delay, or rather the transport lag of the human information processor, is consistently less than when using the instrument to fly than compared when you're flying with the outside world as a guide, right? And these parameters might be invariant regardless of the situation. So that's nice, all right? And we can hence characterize flight across different scenarios, for example, flying a helicopter or flying a fixed-wing aircraft. But this raises actually a challenge to the traditional approach of using cybernetics, because what you might notice from these videos is that the human observer isn't actually flying on the basis of only one channel of information source. Rather, the eyes are always moving, as indicated by this annulus, in order to constantly be extracting information from the outside world. So the fundamental assumptions of a control loop is falsified simply because human operators do not simply extract a single error signal. And because of that, it might be useful to make use of other methods of evaluating information processing in the human, right? Such as eye tracking. So if we perform eye tracking on, let's say, 4 individuals, S1, S2, S3, and S4, ranked ordered in terms of their control performance, what you might see in terms of the likelihood that eye movements from one of these instruments on the display panel and how predictive it is going to result in a dwell on another instrument on the same panel, you would see that eye movements in this case are highly predictive, such that if the eye movement is, if the pilot is currently looking at the airspeed indicator, there's a very high likelihood that he or she will be looking at the attitude indicator next, or the outside world next. So individuals with high performance tend to have more predictive and more organized eye movement behavior than those, for example, who are far worse at controlling a rotorcraft in this case. Now, these transition matrices look very nice, but we could also be compressing it into a single score, namely an entropy score, which I will address next. So the entropy score would be such that for very messy transition matrices like this, you will end up with higher entropy scores, whereas highly organized and highly predictive transition matrices like this would result in lower entropy scores. I'll give you a more concrete example. So this is a highly predictive eye movement scanning across different instruments, and it results in a low scanning entropy score. Whereas in this condition, eye movements are a lot more random, which we have actually experimentally manipulated by making the pilot anxious, and that results in a higher scanning entropy score. Now, how would this entropy score be useful? Well, first of all, let us look at performance, because I like to make a point that performance isn't always indicative of cognitive load on our limited resources. If we simply looked at performance itself, namely our ability to keep to the glide slope of the aircraft, or to keep to the the horizontal latitude of the aircraft, you would see that performance does not consistently get worse, or error does not consistently increase when we increase the demands of a secondary task. So in this case, we would introduce a secondary NBAC task to make the task more difficult for the pilot. And whilst performance might get worse, in this case, with regard to the glide slope, it does not necessarily with the localizer. Okay. In terms of the physiological responses, however, it would also seem that when we increase simply the cognitive demands of the task itself, the heart rate doesn't increase. Okay, so the physiological responses don't necessarily increase, but our manipulation of making our participants more anxious actually work, in terms of when we actually make our participants more anxious by telling them that they're currently being monitored and they're currently being video recorded for their performance, their heart rate actually increases. Now, what I'd like to show you here is that if cognitive anxiety increases, it would seem that eye movement performance does end up becoming a lot more random than if cognitive anxiety decreases. Now, the reason I'm showing this to you is to demonstrate that our ability to extract information from the outside world is not purely determined, it's not stationary. It's affected by human factors such as state anxiety. Eye movements or information uptake can also be influenced by the task demands themselves. So this is a very basic, you could call psychophysics task, where the participant simply has to fixate across in the middle of the screen. And whenever a target appears, let's say a land-out C, they have to make an eye movement as quickly as possible to the peripheral target, okay? And to indicate either move their eyes as quickly as possible, and this is what we call the looking task, or to discriminate and tell if the land-out C is pointing downwards or if it's pointing upwards. And this is what we call the discriminate task. Now, if we look at the saccade reaction times of eye movements in either the discriminate or the looking task for 12 different participants, we would find that simply changing the task demands of this peripheral secondary task can actually vary the saccade reaction time of the eye movements themselves. Namely, that if we know that the end task or the end purpose of moving your eyes is to discriminate a target, we are significantly faster than if we were told simply to move our eyes and to look at this target as quickly as possible. And this is indicated by the scatter plot of data points that consistently fall below the unity line. So how could we imagine how something like this could happen, and what could we, how could we modeling decision making on the basis of saccade reaction times? Well, what we observe in our raw data is a skewed distribution of saccade reaction times for either discriminating in light blue or looking, and we could be modeling them as skewed normal distributions that look like this, okay? Now, these skewed normal distributions arise, or we could say they arise, as a result of an accumulation of a decision signal to move our eyes upon the sudden appearance of a stimulus peripherally, which results in a rapid accumulation of signals, whereupon once it hits a threshold or predetermined threshold, it results in a response, which is our eye movements itself. So this is the end result of what we can actually observe from eye movements, which belies the rate of accumulation of a decision signal or the threshold beyond which an eye movement is executed in the first place. So now we have two parameters, the threshold or the rate itself. Based on the data that I've shown you previously, if we try to fit the decision-making model, or this thing in between, for either the threshold parameter or the rate parameter, What we might infer from this data of this experiment is that this rate or this slope is actually higher for in the discriminate task compared to the looking task, whereas the threshold remains the same regardless of the task itself. So what might be suggested from this study itself is that the task or the urgency of the task that we're working on might actually motivate or increase the rate at which we have to make a decision, or if you will, if you fancy the notion, an increase in the firing rate of decision-making neurons, if you will. So the point of the first part of this talk is to show that we do not passively process an error signal as might be characterized by a pure cybernetic approach. There's a lot more going on. The human operator actively seeks out information, and the available bandwidth for information uptake is limited. And we've known this for a long time, just simply based on the hardware of vision itself, the sensor itself, right? But what we need reminding of perhaps is that human factors significantly influence our ability to direct information uptake, to move our eyes around. And such human factors aspects could include state anxiety, the task demands itself, and the expertise of the human operator. So here's an example, and I hope you can see the video, of how we might be guiding information uptake using technology. So what you see here is a system that displays for the person who has to assemble a piece of equipment over time, which piece to pick up, okay, at which given point in time. Okay, so users of this cyber-physical system often report that the workload is lower than what they normally experience if they have to refer to an instruction manual, or if they have to refer to their memory of how to assemble a complex system. Now, on the basis of this, we might then ask ourselves, well, could we be quantifying or giving a better definition as to what this so-called mental workload might be? So as psychologists, we might say, well, based on the qualitative interview reports, operators are saying that they find that this system requires them to remember less information because it provides them with just-in-time information, right? So one way of measuring working memory would be perhaps to make use of EEG systems and to look at a metric, namely the power that falls in the so-called alpha bandwidth between the frequency bandwidth of 8 to 12 hertz. So if we do this and we compare between operators who are either performing this assembly task on the basis of this cyber-physical system, on the basis of paper instructions, what we do find in general is that the projection system results in higher alpha power, which is indicative of less working memory load, so to speak, compared to if they had to rely on paper instructions instead, all but for participant 9 and participant 11, for example. Now, it's interesting here, and this is just an association, mind you, that participant 9 and participant 11 actually qualitatively reported that they didn't like this projection system at all. Rather, they actually felt that the projection system was very stressful because it felt like it was telling them what to do at a very high speed. So they actually found the paper instructions less demanding because they could actually pace themselves. Okay, but this is only associative and anecdotal evidence. Other aspects of technology where we could be saying, well, how about we control how information is uptake could be something like this, where we are facing a future perhaps with smart watches, where we might need to read papers perhaps on our smart watch. And that is certainly not viable. But what we could be doing instead, let's see if this video works. What we could be doing instead is we could be borrowing a concept from psychology, namely rapid serial visual presentation, to be presenting text as a rapid serial visual presentation of the words drawn from the text in order to read, right? Now, such a system is not new and has been recommended since the 80s. It's claimed to be to reduce reading times simply because it cuts down on the amount of time that you need to move the eyes, but it also cuts down on the amount of workload, so to speak, of planning your eye movements to know which word to pick out next from the text. Now, what you see over here in different colors are essentially the theta power of our participants when we presented them with these RSVP readers. Okay, in this case, what you would see here is rather the theta power from the EEG measurements of 12 different participants. I believe it's 12 different participants, as ranked according to their speed gain factor, where it shows that if your participant actually gains a lot of speed out of the RSVP reader, they actually experience lower theta powers. And in this case, lower theta power is indicative of less workload, okay? So the reason I'm showing this is because I think there is still quite a bit of work to be done in terms of individual calibrations, especially for these wearable readers, because it's not universal that everyone finds them easy to use. And perhaps EEG could be, or physiological measurements could be a way of enabling for calibration across larger populations. This is another way of displaying information, for example, with aviation vehicles, to cut down on the need for eye movements, if eye movement planning is indeed a vulnerable point for information uptake. We're currently working on a project where, with the use of smartphones, we could be looking around in our environment to enable people to learn difficult aspects of a foreign language, such as, for example, with the smartphone, it might detect that these are the objects in the environment, and to then, with the use of translation machines, to be indicating the propositional relationships and the case grammar of German between these different objects. And if you're interested in trying this out for yourself, you could download this app on your smartphone to see how we might be able to make use of computer vision to learn languages in our everyday environment. So enough about perception. I'd like to switch gears and talk about cognition and how I might be proposing that we could be making use of neurophysiological or rather electrophysiological measurements of the human operator to make to gain some insights, not just about information seeking processes, but information processing in cognition itself to generate new knowledge. Now, once again, if we take a pure control perspective of how individuals might be controlling machines, it would not help us understand aspects or psychological phenomena such as inattentional blindness or inattentional deafness. Now, what you'd see here is that with the introduction of heads-up display, this was the perspective that if the error signal was the thing that we care the most about, then why don't we just have a heads-up display that shows the error signal in high detail? Now, what human factors specialists realized after introducing these heads-up display was that they introduced a new problem such as inattentional blindness, namely pilots failed to recognize unexpected events which they considered to no longer be relevant, such as the unexpected appearance of a potential collision target on the landing strip. Inattentional deafness, which I don't think you can hear because of Zoom, occurs when during flight, alerts or auditory alarms go off that the pilot does not expect, and they actually fail to hear this, okay? So inattentional deafness has been found in a study to occur in 11 out of 28 highly trained pilots. They failed to notice a critical auditory warning that told them that even if they managed to land, their landing wheels will not deploy, okay? So the appropriate action for these pilots was actually to abort their primary task, which was to try to land the plane in very windy conditions, to abort that sequence completely. But they were so fixated on the primary task that they persevered with the primary task, not realizing that if the wheels didn't land, because this alarm, auditory alarm was going off, they would actually be crashing the plane. Now, further studies into this phenomenon of inattentional deafness in pilots and average human subjects have shown have localized this this dysfunction, so to speak, in areas such as the inferior frontal gyrus, for example, okay, or the presensory motor cortex. So our lab also looked at inattentional deafness, but with a slightly different perspective, which is to say, well, could we be indexing the demands of a control task by pinging the human operator with irrelevant sounds, okay? So what we showed was that the control demands of a control task in trying to pilot a aerial vehicle actually weaken the brain response to sounds in the environment that participants considered to be completely irrelevant to the task. So while someone was trying to pilot an aerial vehicle, they might be hearing sounds such as a cat meowing or a baby crying, which they were not required to respond to at all. Now, but just because we tell the participants that they don't have to respond to these sounds does not mean that participants do not respond to these sounds in terms of their information processing system, right? Because if we look at the EEG that is elicited from the appearance of these sounds, you will see your involuntary auditory evoked potential that looks like this. Okay, whenever a cat meow or a baby crying or a dog bark occurs, you will see your auditory evoked potential. But more interestingly, when you have to steer this aerial vehicle, certain, not all, but certain evoked potentials in this waveform is selectively decremented. Okay, the amplitudes are decremented when you have to steer in green compared to when you're just a passenger in this aerial vehicle. So just simply requiring someone to steer a vehicle results in them having less attention, so to speak, to their task irrelevant auditory environment in these time periods of the evoked potential waveform. If we have a look at the parts of this waveform that are selectively attenuated, we might, from psychology, make some subjective inference that these potentials might relate somewhat to our ability to have our attention captured, so involuntary reorienting, or perhaps with regards to context updating. We've done a couple of experiments where we controlled as to whether or not the auditory channel was relevant or irrelevant, and we found that making the auditory channel relevant selectively increased this late novelty P3 in the same task as well. But I mentioned earlier that perhaps we could be making use of these task irrelevant sounds as a way of estimating workload or estimating the effects of our information processing resources in this human operator itself, right? So let us assume that our capacity for information processing in a human is limited, and this resource pool might shrink when the demands of this control task increases, to the extent that that the responses to irrelevant environmental sounds are attenuated. That means that we can be regularly pinging the human operator and evaluating to see what responses come out of it to determine how demanding this control task is. And we could be manipulating different aspects of this control task to see which aspects of controlling this machine actually lowers our attention to the auditory environment. So we could either be manipulating the goal predictability, which in your everyday life might be characterized as driving on a straight road. So driving on a straight road is highly predictable, whereas driving on a road that constantly changes direction is less predictable. So if you ask someone anecdotally, they would say, well, driving on a straight road has less mental workload than driving on a road that constantly changes direction. Now, if we look at the evoked responses to irrelevant environmental sounds, we would see that this does not affect the evoked response amplitudes at all. If we manipulate the vehicle dynamics instead, such as can be characterized as driving on a non-slippery road compared to driving on a slippery road. I won't go into details as to how we manipulated the vehicle dynamics, but we can discuss this further later on. We would once again see that this selectively targets the late novelty P3 response to the appearance of seemingly to the participant task irrelevant environmental sounds. Okay. So we would suggest that this late novelty P3 amplitude could be a way of indexing the executive demands of a control task, the ability to predict future trajectories or future consequences of control, or what might be operationalized as situational awareness level 3 by Mika Ensley. I spoke earlier about human-machine partnerships, and we might be entering a time where sensors around the vehicles could be informing us and giving us notifications of surrounding pedestrians, other cars, or navigations, which then raises the topic of, well, if these sensors around the vehicle are capable of detecting all these different objects, how should they be alerting the human who's in the loop of controlling the vehicle itself? Now, one type of an auditory notification that we've played around with is to manipulate the sound to either be a constant stationary sound for which the amplitude doesn't change at all, or a looming sound that whereby the volume or the intensity of the sound increases across time. To cut a long story short, the psychophysics of it is such that if I'm controlling, if I'm performing a manual tracking task and I hear a looming sound, the effect of the looming sound in reducing my response time to discriminating these Gabor patches are significantly, we are significantly faster in discriminating for these Gabor patches with the provision of these auditory notifications. But the looming sound seems to result in a sustained advantage of this reorienting to a peripheral target compared to a uniform, a static sound, or a receding sound. So it seems to be longer lasting. Hence the recommendation of the use of looming notifications. But if we make use of EEG to understand the basis of this advantage, we might actually see, or we did actually see preferential activity in two regions, or in at least two regions of the human brain, so to speak, whereby the constant sound resulted in larger intensity, so to speak, compared to the looming sound in Brodmann's errors 8, okay. Or the sensory motor cortex, or we might see larger intensity in our ERPs, in this dipole when it's motivated by a looming sound relative to a constant static sound instead. So we are looking into this further as well, especially in the context of applied scenarios, such as the use of such sounds to prompt a user of an automated vehicle to perform an emergency braking in some scenarios. Okay, so here's the performance, the behavioral performance again, where we look at the braking times, where the looming sounds result in much faster braking times than if you present a static sound. But if we look at the EEG response to the appearance of these looming sounds, we actually see differentiated activity in the dipole located especially in Brodmann area 8. Okay, so EEG contrast reveals that there are differences between the static and looming sounds that might correspond with our ability to brake much faster when hearing a looming sound. I'm going to end this talk by talking about an applied scenario where we had a collaboration with the trucking industry to look at what kind of auditory notifications they might start employing in their cabins. Okay, so the trucking industry accounts for 70% of US freight, and there are lots of accidents that go on, which creates a sub-industry of what kind of auditory notifications should we be presenting to truck drivers. Especially in the event of the use of automated driving, which could reduce the vigilance of truck drivers. Okay, just to give you a sense of the shortfall of truck drivers, the pay of a truck driver is about $73,000 per annum in the US. And this is a bit of a reality check for many of us, which is the average salary of a postdoc in the US. Okay. So when we first spoke to our partners at Scania, they told us that of all these sounds that were kind of proposed to be used as auditory notifications in the truck cabin for different purposes, the auditory designers always came back to them to recommend the use of verbal notifications. So to make use of human voices that said things like traffic or stop or beware, right? And the rationale for this was that these auditory designers made use of performance measurements such as percentage correct in discriminating between these different sounds, as well as response times. So the take-home message from this is that auditory notifications that are verbal result in more correct discrimination and much faster response time. But this does raise the question as to, do we really care about speed and accuracy for supporting strategic and operative decisions in a truck cabin, especially at the scale of about 1 second? Is that really that important, operationally speaking? Right? Which is why we decided, or we proposed, that why don't we do an EEG study on these different auditory notifications that have already been designed, to have a look at how we might be responding to these different sounds as designed by by audio designers. Now, the nice thing is about this, about our information processing system, is that we all seem to share a very similar nervous system, such that that the evoke response from mature Swedish truck drivers do not differ very much from young German undergraduates, right? So this waveform looks very similar. We see very similar evoke potentials in both cases. Now, coming back to the earlier assertion that verbal notifications were better, okay, than iconic sounds. Well, that might be true if we care about early processes of discriminating a notification from the background or attentional capture. But if we had a look at the responses from auditory icons, such as the sound of a raindrop to indicate approaching storm or inclement weather, we would see what psychology theories might already be hypothesizing or predicting, namely that such sounds are much better in updating for the context. So a more nuanced recommendation on the basis of looking at the EEG responses to auditory notifications would be that perhaps we ought to consider using verbal sounds when we need to issue emergency warnings, things that needs high discrimination from the background or high attentional capture, whereas we ought to be making use of auditory icons when we need to be updating the context of the operator themselves. So as a very quick summary, electrophysiology might provide insight into information processing. It's indicative of inattention to irrelevant information, and irrelevant comes here with a question mark, because how do we know if something is irrelevant until we've actually processed it in depth, right? And that's, of course, something that I believe interests many members at IFADO in terms of the role of attention and the depth processing of different information. How do we select different information for different depth of processing? electrophysiology could be used for the evaluation and the design of notifications. And depending on the operational objectives or the situation that we're evaluating, it could actually be a lot more meaningful than performance measures themselves. So we're rapidly entering a time that as technical problems become more and more automatic, the people problem become more and more surrealistic, right? So it might be important for us to be looking at these covert processes of information processing to try to understand what on earth is going on when we actually come across or experience information, and behavioral measures themselves might not quite make it. So to conclude, engineering is rapidly transitioning from human-machine control to human-machine partnerships, and designing these partnerships require us to know how humans process information before we can actually outsource this to machine automation. Performance alone is not diagnostic of human information processing, and implicit measurements of the human nervous system could in some cases be a lot more meaningful. I've been asked many times this month in terms of what I actually intend to do in my academic career, and or what I intend to do at IFADO, but it gave me purchase to think about what I actually want to do in my research or academic career in general, right? And I refer us to this resource, this great bibliographic resource, Twitter, where I answered Will Gervais recently, where he asked, what's the big question that drives your research in a sentence or two, okay? And it forced me to think about what I really want to do. And the really big question that I'd like to work on is whether or not we can verify if information has been effectively transferred from a machine to the human operator and back again. Now, I spoke earlier that when I was a PhD student, I worked on real fundamental questions like visual object recognition, what counts as real information in our complex visual environment. So when I actually had to work on applied problems, I wasn't the happiest person, I'd be honest here. But it turned out that actually working on applied problems gave me the ability to think about what exactly counts as relevant information in this current context, right? It allowed me to actually quantify information itself, rather than to wonder if visual information is best characterized by Gabor orientations or frequency bands. So it gave me some traction to the question, right? So this is why I'm quite excited and still am excited to work in the applied aspects of psychology or engineering psychology, because I actually think that it makes the problem of understanding what information really is a lot more tractable than if we worked with so-called naturalistic environments. So here's a very quick acknowledgement of people I've had the privilege of working with, whose work I've actually talked about today. So I'm happy to take any questions or comments. Thank you very much.
Thank you, Louis, for this wonderful talk. And I don't think there was that much overlap compared to the talk that you gave like 2 years ago. I think there was lots of new stuff. Thanks so much for sharing. I'm going to stop the recording now.